In section 9.6 here, we're going to be taking a look at the binomial expansion. Now, the binomial is exactly what it sounds like. Let me grab my pen here. We can multiply. Binomial is two terms by. So we're multiplying this times itself. We would FOIL it out. We'd get x times x times y times x, y times y. So what they've discovered here is one of the more interesting ideas in mathematics, that this works out. But there's a pattern, a formula that begins to emerge when you keep multiplying binomials time themselves. So obviously here we start with x plus y to the first power, you get the same thing. But now x plus y to the second, we're going to FOIL like we did here, and this is what you'd get. Well, if you added a third piece onto here and FOILed the first two out and the first three, we get this. And as someone continued to expand these, keep successive binomials multiplied by themselves over and over again, they saw this pattern begin to develop. And here's what we have. So x plus y to the first power, you get just what you started with, but you get two terms. You get the first one and the second, because it was a binomial, so you get a binomial. Now, if the exponent goes to the second, you keep getting one more term than you had exponent. Do you see now, if we had x plus y to the third, we get one more term. We had the third power, now we have four of them. Now we do x plus y to the fourth, we had to the fourth power, and now we get five terms. So we keep getting one more term than we have exponent, which is what this is saying. And then, if you notice what's happening is, let's go down here to this one. So we're going to wind up with three x's, and then the x's are going to start going down, and the y's are going to start going up. So 3x's and no y's, 2x's and 1y, 1x and 2y's, 3y's and no x's. So the x's are going downward, the y's are going up. So they noticed this kept happening, and they established those patterns. And then they noticed something interesting as well, that the coefficients in front of each of the terms began to follow something called Pascal's triangle, where what we can do is each value here is the addition of the two above it. So if you drew a diagonal, this is 1 and 2 make 3. 3 here comes from 2 plus 1. 3 plus 3 make the 6. 1 and 3 make the 4, etc. So this pattern just keeps repeating itself all the way down the triangle. So we can establish, just from the fact that there's a pattern, someone began to see how they could expand them no matter how many exponents that you had, by following Pascal's triangle and following these tricks about the number of terms and the exponents. Now, what I think is fascinating is that this turns out, the way this can be arranged, these coefficients turn out to follow a combination. So let me show you what I mean. So each of the coefficients in front of the terms is found by using a combination of this many. Let me go back here. Well, let me refresh you. Let's just talk about a combination here real quick, and then I'll show you how it fits into the formula. So do you remember this pattern from our probability section? This is a combination. You take n objects, and so it's n factorial, and then because it's a combination here, and this part takes care of how many terms you're doing, n factorial, and then this drops off. So if we had 5 taken 3 at a time, we did 5 factorial divided by 5 minus 3 factorial, and then this part took care of the repeats. Do you remember that? So I won't rehash that whole video here, but my point is that we've seen this before. This is a combination. So we can find the coefficients from each term by following these. Now, it's not written combination 5, 3. This is an equivalent way of writing it. This means combination of 5 taken 3 at a time. So it doesn't look the same, but it means the same thing. So on my calculator, like if I was doing this one, if you go to math and then over to probability, you do 5 combination 3. Is how you'd get the 10. Or you could do the math yourself. Let me double check, make sure I'm right about that. Yeah, hit math on if you got a TI, go over to probability, and then for me it's number 3. It's NCR. So it's standing for combination. How many did you have? How many are you taking at 3 at a time? So this is a combination notation. This would be 9c2. And this, of course, would be 9c7. So make sure you can crunch those because we're going to need those. This is how we get the coefficients in front of this binomial expansion. Okay, so on my calculator I would do 7c3, or you could do the math, but there's so many of these. I'd recommend you do the calculator. And then you've got 11c4 for the second one. Crunch those out. You should get 35 for the first one, 330 for the second. Okay, now here's this binomial theorem. That it looks crazy, but we can find how to expand any binomial because it follows this pattern. Now, this pattern may not seem like anything. I'm not going to try to talk through all that madness. Let's talk it through. Here's what it's saying. So we're going to expand this. So here's what's going to happen. What we're going to do, our exponent is 5, so n is 5. And then we're going to just walk our way through. So we're going to do 5 taken 0 at a time, 5 taken 1, 2, 3, 4, 5, till we've exhausted all the possibilities. 5 taken 0, 5 taken 1, 2, 3, 4, 5. And then this down here is r. So we're going to make r 0, then we're going to make r 1, then we're going to make r 2, 3, 4, 5. We're going to do every possible combination that we could create. These are all the coefficients of the terms. Now, look what happens with the variables. We have x to the 5th, and we don't have any y's. Then we're going to lower that. Now we have x to the 4th, and we have a y. X to the 3rd, and we have 2 y's. X to the 2nd, we have 3 y's. So we're going down with the x's and up with the y's until we've covered all the possibilities. Now, instead of trying to FOIL x plus y out all this many times, this tells you the entire expansion of this binomial to the 5th power. We do the combination here, that's going to be 1. Where's my pen? This is going to turn to be 1. Y to the 0th is 1, so we get x to the 5th. Now, we crunch this on our calculator, and this is going to be 5. X to the 4th, y to the 4th. This combination, 5 taken 2 at a time, is going to get you 10. Again, this is Pascal's triangle, but you don't have to memorize this. 5 taken 3 at a time gets you 10. The x's are going down, the y's are going up. We can create the whole thing. Now, look at a more difficult one here with b. So our exponent is 4, so n is going to be 4, and we're going to start with r being 0 all the way up. So let's just start with that. We're going to have 4 taken 0 at a time, 4 taken 1, 4 taken 2, 4 taken 3, 4 taken 4. Now, what's a little different here is the first term, why does my pen keep disappearing? There it is, okay. The first term is not just x this time, it's 3x. So we're going to have 4 3x's, then 3 3x's, then 2, then 1, then 0. And while that's going up, our second term, which is now negative y, is going to have 0. Then it's going to have 1. Then it's going to have 2, then 3, and then 4. Now, crunching these is not going to be that easy, but we're going to do 4 to the 0, well, 4 taken 0 at a time, then times 3x to the 4th. So we just have to crunch this math now. Now, I know this doesn't look simple. It looks totally crazy, but this is a whole lot better than foiling these out. Yeah, otherwise you'd have to do 3x minus y times 3x minus y times 3x minus y. So this is a clever way to expand a binomial based on this formula, this pattern. Okay, so let's try some of these. So we've got it. Notice here we've got negative y. So here's what we've got. Our exponent is 5. So we're going to have 5 to the 0 and 5 to the 1. 5 taken 2, I should be saying. 5 taken 3. 5 taken 4. And 5 taken 5. I gave myself not enough room. Okay, now we're going to have 5 x's and 0 negative y's. Now that second term is negative y, so don't lose that. Now we're going to have 4 x's and 1 negative y. Now we're going to have 3 x's and 2 negative y's. We're going to have 2 x's. You see we're just stepping down. 3 negative y's. We're going to have 1 x, 4 negative y's. We're going to have 0 x's. I'm not going to write it because I'm out of space. We're going to have 5 negative y's. Okay, now this is a lot of work, but 5 5C0 is how I would do this first one on my calculator. Then we're going to do 5C1, 5C2, right on down the line. Okay? So here we're going to have, I don't know if I want to crunch all these. Let me just talk you through this one. So 5 to the 0 is going to be, we're taking 0 at a time. That's going to get me 1, and x to the 5th. Now this is going to get me 5, and then x to the 4th, negative y to the 1st is what created that negative sign right there. Now this is going to create 10. I've got 3 x's. Negative y squared is going to, the two negatives, when you square this, will drop out. That's how we get the y to the 2nd. We'll do one more of these. This creates 10 as well. If I have 3 negative y's, negative y times negative y times negative y is where I created that negative, and so on down the line. Now I don't know if I've done this here. Okay, I did, but so let me just show you the setup. So let's do one where the terms are a little more complicated. So we've got an exponent of 3, so we're going to start with 3 to the 0. 3 taken 0 times. I'm going to just step my way through all of these first. 3 taken 2, 3 taken 3. Okay, I don't know if I have enough room here, but now we're going to take that first term 5 times, and we don't have any of these. That's just going to become a 1. Now, we're going to take 2x. Now there's, oh, sorry. Shoot, I messed this up. Hold on. Our exponent was 3, so 2x to the 3, 5y to the 0. 3 taken 1 at a time. Now 2x is going to step down to having 2 of them. 5y is now going to have 1. 3 taken 2 at a time. 2x is now stepped down to having just 1. 5y is now stepped up to having 2. And there we go. So we're stepping down. So anyway, just keep following that pattern to do the different versions of the combinations. We start with the first term to the third exponent, step its way down. We take the second term to the 0, and he steps his way up. Now we can crunch all this. I'm going to just show you here. So this is going to create 10. Hold on. Oh yeah, I'm sorry. This is all to the 0th power, so 5y to the 0, that's just going to all become 1. So this is going to be 2 to the 3rd power, creates that 8. Just look at one more of these here. 3 taken 1 at a time is going to create a 3, so we've got 8 times, 4. So it's 2 to the 2nd. Now this is going to create 4 times 5. This gets 8. Hold on, I got to do this one. I'm not sure I'm saying that right. Let me see. Yeah, no, it is 3. So this should get you 2 to the 4th. 3 times 4 times 5. There we go. Okay. Okay, so we're just crunching all of these. Sorry, I had trouble with this. X to the 2nd, y. Yeah, so here's my 60x squared y. Just keep going through here. This is a mistake, sorry. There. Okay, now just one last idea here. We could, instead of expanding the entire thing out, what we could do is we could just find the particular term that we're interested in. We're just going to find it for a particular value. Now, instead of talking this through, let me show you with an example. We want to find the 10th term. Now, the trick here is that r has started with 0. So remember how we did this? We did n r. Like, so if the exponent was 16, we'd have 16, but our first term would have had an r of 0. And because there's an r of 0, we're going to need to keep that in mind. So this is what we want to do. And to find the 10th term, well, if r started at 0, we have r plus 1 is the 10th term. So there were actually 9 in the r. So because we started with 0, we want to find the 10th term. It's r plus 1 equals the 10th term. Again, we're adjusting for the fact that we started with 0. So the r that we're going to need in our calculations is going to just solve that. We're going to have r is 9. Okay, so if we want to find the 10th term, we actually need an r of 9. What you're going to do is you're going to subtract the highest exponent's the 16. We're going to take away that r, and then the second term is just going to be to the rth power. So 16 taken 9 at a time. Again, we adjusted. So we want the 10th term, but we want the 9th r because of the fact r starts with 0. Now this is going to be the highest exponent, which was that 16. Take away the r. And this here is going to be the second term to the rth power. Okay, so here we go again. So we want the 6th term. So it's r plus 1 equals 6. So we're going to want to use an r of 5. Again, it's adjusting for the fact that this starts with 0 when we expand these. So the 6th term is going to be 9 taken 5 at a time. We're going to take that exponent, and we're taking 5. We're using r. So then we're doing 3x to the 9 minus r times negative y to the r. Now, you could have expanded the whole thing out, but with such high exponents, this would have been really time consuming. And what we're doing is just getting a shortcut. Again, we're adjusting. We want the 6th term. So we want to adjust r for the fact that we want the 6th term, which means take away 1. So r is going to be 5. Again, this is because r starts with 0. So this 6th term is actually 9 taken 5 at a time using r. The first term taken 9 minus the 5. The second term taken to the r power. Okay, so crunch this down. You would do 9c5 on your calculator. You'd be doing 3x to the 4th power, negative y to the 5th power. Hold on, let me see what 9 taken 5 at a time is. I get 126 here. Okay, we keep expanding this. You're going to have 5 negative y, so that's going to make it negative 3 to the 4th power. So we've got, hold on, let me just do that. So 3 to the 4th power, of course, gets me 81. So 81 times 126 gets me this. But it's a negative because we have negative 1 times negative 1 5 times. And there we go. Okay, so that's the binomial expansion. So a clever little shortcut for expanding a binomial to any exponent that we want.